Hello everyone, I am Paramita. On behalf of my co-authors, I welcome you to the talk on our paper titled Quality Change, Norm or Exception, Measurement, Analysis and Detection of Quality Change in Wikipedia. In this work, we have rigorously explored English Wikipedia quality life cycle from the perspective of various quality indicators and proposed an unsupervised approach to detect the quality changes. This is the snapshot of the talk page of this article, Social Networking Service. This article is assigned to quality class B by all the wiki projects to which the article belongs. So what is article quality? It denotes how good an article is. Ideally, it should be comprehensible, well-organized, readable, and well-referenced. In English Wikipedia, there exist 7 quality classes, FA, AGA, BC, Start, and Staff, in descending order of their quality. This figure shows how an article's quality has evolved through different quality states over time. But is it always true that quality changes through one-way promotion only? Can there be demotion as well, or any other kind of temporal patterns? Here comes our research question. Our first research question is how do Wikipedia articles transition through different quality steps? We will show various temporal transition patterns and their analysis emerging from this research question. Our second question is, if such patterns exist, then how to detect the quality changes automatically and intimate the editors at right time? Our dataset comprises 30K English Wikipedia articles and 7 quality classes. For the ease of computation, we mark quality classes which are approximately equivalent in terms of qualitative features. Now I will show a few temporal patterns emerging from the analysis of quality evolution of articles. According to our analysis, we have found 4 types of quality evolution in the quality life cycle of articles. This table tabulates possible types of promotions and their statistics. For example, SS to FA in this category, in which the articles are promoted from lowest quality SS to highest one FA. And the average time taken for such promotion is more than 3 years, whereas the promotion AGA to FA took less time. Similarly, this table is showing possible types of demotions. Surprisingly, we observed that around 51.72% articles in our sample dataset have gone through quality evolution only once in their lifetime. For example, FA pages took the highest time gap to evaluate it first time since its creation. This proves that majority of these articles are overlooked by the present manual assessment scheme, which is not a healthy sign for this platform. Also, 1407 articles in our dataset have gone through both promotion and demotion in their lifetime. These 2 figures are showing a visual illustration of temporal changes in quality classes into different time windows, 2010 to 14 and 14 to 19. The 2 figures clearly depict that often the intra-class quality remains the same over time, except a few inter-class quality exhibit a change. We have observed another temporal pattern, which is the cyclic change of qualities. Here an article P is assigned to class AGA, then got demoted to BC, and then further promoted to AGA in its life cycle. We found that around 1286 articles in our dataset exhibited one or more cyclic switches. We identified quite a few rapid cyclic switches whose turnaround time for the cycle is less than 15 years. We mark it as extremely non-trivial behavior and attribute as a quality switch word similar to the famous phenomenon edit word in Wikipedia. We try to understand how features are exhibiting temporal trends at the point of quality change. Here the red line indicates the change point of quality, but a page is demoted from FA to some lower quality. Here, in case of this feature, number of distinct editors editing article's main page, if we consider 4 consecutive timestamps on either side of the change point, the change is served on both sides. This indicates that a large number of editors were active when the pages reached to the FA status, but many of them stopped editing after the demotion in quality. The same trend can be observed in case of number of revisions and the length of articles. So far, we observed various kinds of temporal patterns revealing the dynamic life cycle of article quality. Our next task is to detect such changes to identify the possible quality change. To resolve this problem, we experiment with change point detection algorithms and propose our novel unsupervised quality change detection approach. We applied these multivariate CPD algorithms. Each of the algorithms works on optimizing the cost function, and the objective is to minimize the time gap between the ground truth and detected quality point. In our settings of quality change point detection, we formulate the analogy as follows. Individual article is assumed as separate time series and the timeline is expressed in months. The sample data points are the latest revision each month given an article. The change points are the time instances, specifically the months where the quality of the article were changed. Now, every such time instances or revisions are represented by these features. For more details of each category of features, please visit section 5 of our paper. To examine the relationship among the different features, we compute the Pearson correlation coefficient between all possible feature combinations that is shown in this heat map. The first 6 features are contribution-based features. Next group of 8 features are activity features. Finally, this last 20 features belong to the content-based features. As we can see, for almost all the features, the coefficients are in the range 0.2 to 0.9, except the closely related features like F4 and F5. In content-based features, the readability features are semantically related, hence showing high correlation, except the feature F26, which is the feature denoting difficult words. This is the schematic diagram of our experimental setup for the change point detection. For the page P, every last revision of every month is represented by 3 types of features. Thus, these revisions altogether constitute a time series which is fed as input to the CPD algorithms. The outcome for each page is evaluated by the metric covering precision and recall individually. This is the result we obtained from our experiment with 3 key CPD algorithms and 1 additional method hybrid, which took the maximum value for each metric as reported by the 3 algorithms in their best hyperparameter cities and averaged over sample test cases. We achieved best covering 0.6 from BSEC. The best result for ECP and PELT are 0.6. The highest achievable precision and recall are 0.6 for BSEC and 0.61 for PELT. As expected, the content-based features along are sufficient to produce the best results. The hybrid method achieves the best covering precision and recall among all the 3 methods. Let me brief a few key points of our proposed methodology. It's clear that the content-based features achieve the best performance. Further, we tried rigorous evaluation study, and on the basis of heat map, we ran CPD algorithm for groups of few selected features irrespective of categorization of features, and have seen that a selected combination of activity and content-based features attains superior performance. Overall, we identified the following influential features that played a significant role in the detection of quality change point, which points to the importance of organizational characteristics of such a large peer production system. We compared the performance of our proposed methodology with the popular tool of Wikipedia Foundation, which is ORES. ORES is a web service or API designed for Wikimedia projects to provide an automated solution for critical wiki works, and quality prediction is one of such tasks. We managed to compare the 2 settings and observe that our hybrid CPD algorithms by far outperforms the results obtained from ORES for both these sets of articles. Finally, I want to mention the key success of our study. Through our rigorous micro-level analysis of 30K articles along with the complete article edit log, text page, and talk page of both over the duration of almost 14 years, we are the first to reveal the article quality is not just a static measure, rather it evolves through different dynamic states such as promotion, demotion, no change, both promotion and demotion, and quality switches. Our longitudinal analysis discovered that a large fraction of articles do not have subsequent quality change after the first shift, which means the quality change of Wikipedia article is more an exception than a norm. With a series of very intuitive features, we are able to obtain decent scores in detecting upcoming quality changes. This modeling can show the way to the design full-fledged alert systems for the Wikipedia community for timely decision on quality changes. Thank you for taking time to attend this. I hope you read our paper. Please feel free to contact us for any query.